Hello. So I guess we can get started. And my name is Weixi. I'm currently an OS technical expert at Huawei, and I also contribute to the OpenOLA community. My talk today would be GMEM, which is in short for Generalized Memory Management, and we are doing this for accelerators. So as you guys know, this is currently a golden age of accelerators, and you can see a lot of AI applications, including the GPT-4, robotics, databases, or maybe other DNA sequences, some kind of tasks. And these applications are actually supported by these, including the GPUs, the TPUs, or other DSAs. So before I'm introducing GMEM, here's a little bit history about GMEM and what we're going to do in the future. The original idea of GMEM was originated from my PhD study at Rice University, where I worked with both my advisors, Scott Rixner, who is an expert at the microarchitecture field, and my other advisor, Alan Cox, who is a kernel maintainer for the FreeBSD community. So I was able to look at the idea from two aspects, both from the microarchitecture and from the OS design principles. And we decided that GMEM would be the heart of OpenOLA's OS for AI. And there would be a Linux-based version soon to be available in the early October. So memory is indeed the core of AI infrastructure. As you can see, the AI and heterogeneous applications would require CPU coordination because the domain-specific accelerators cannot do all kinds of jobs. We still need to use the general-purpose CPUs to do other tasks. At the same time, they require a huge amount of memory to process a large volume of data. And they need quite fast memory allocation speed and high memory utilization because HBM is so scarce. As you can see from the Hopper GPU, which is the most advanced accelerator, I guess, at this moment, it only has like 100 gigabytes of HBM. However, the reality is actually bad because the accelerators, we have poor programmability. If you guys have written any CUDA applications, you know that you need to allocate your CPU buffer and at the same time allocating your GPU buffer and transfer this data between the two buffers. At the same time, we have this out-of-memory problem because accelerators have small HBM capacity. And also, these AI frameworks, they develop their own malloc and free library. But this reimplementation does not really function well. And we see a lot of memory fragmentation issue in these AI frameworks. For example, we see this failure of mallocing 500 megabytes memory, given that the accelerator still has 10 gigabytes of free HBM. So if we dig a little bit deeper, we can see that here is the cost of reinventing the malloc library. And by malloc library, here I mean that typically we can use like tcmalloc from Google, or jemalloc from Facebook, ptmalloc from glibc. We can use all of these malloc libraries for the CPU applications. But when it goes to the AI framework, the underlying memory service cannot be provided by the operating system. So like PyTorch, TensorFlow, they have to implement their own library. And if you take a look at them, they span around like 4,000 to 6,000 lines of code. And do they really work well in reality? So we make a comparison between PyTorch and jemalloc using the same workload from a large language model. And we see that the malloc latency from PyTorch is around 1,000 nanoseconds, while it is 300 nanoseconds. So it's like 3 times slower from PyTorch reimplementation. So things could be even worse when we look at the underlying memory management subsystem. So we first take a look at what does the kernel do? The Linux core MM has 80,000 lines of code, while the FreeBSD has 30,000 lines of code. And well, this is kind of common because FreeBSD is more of a academic view of the operating system. So the lines of code is like fewer. But when it goes to device driver, for example, NVIDIA's CUDA driver, it spans like 100,000 lines of code, and 30,000 lines of code from its GPU MM, and 70,000 lines of code from the UVM driver, supporting the kernel level swapping. And we also take a look at the AMD driver and Huawei's ASUN driver. They share like similar magnitude of memory management code. And we would have this doubt that whether these memory subsystems have bugs, system overhead, or memory fragmentation issue. Because the memory management system is like very complicated, and it has been evolved over a long time in the operating system, but accelerators are quite new. So this really ultimately gives us the motivation of GMEM. And the first motivation is that we want to stop people from further reinventing the wheel. And this includes two aspects. One is not to implement any more malloc library for your GPU or TPU or whatever. The second is not to re-implement any memory management systems for your device drivers. And secondly, we want to enhance the programmability of the accelerators, as we are going to provide a unified virtual address space so that your pointers can be shared between your CPU and accelerators. And at the same time, we will allow your application to oversubscribe your device memory so that you don't need to write any lines of code just to, like, you can even use 1 terabyte of memory even though your HBM is like 30 gigabytes. And ultimately, we are going to provide better memory service. This includes both faster malloc speed and higher memory utilization. So before we are looking at any kind of design, we want to ask the question like, why can the operating system manage any accelerator's memory? And to answer this question, ultimately the memory subsystems are all the same. Because if we divide the design and the implementation of all the existing memory management subsystems, we can see that there are 4 components. The first 2 components are virtual address allocation and deallocation, while the second, and as well as the physical address allocation and deallocation. So you guys might be familiar that the first part is basically about your M map or MR map, and the second part is mostly about your body allocator, or transparent huge page, which is more complicated, but ultimately they are the same. While the last 2 components, the virtual to physical address mapping management and the physical data preparation, they involve hardware-specific handling. So if you are using a CPU with a different microarchitecture, for example, the x86 or ARM or whatever else, or you are switching to a GPU card, for example, in NVIDIA, you may use Pascal or Hopper or Ampere or whatever, the underlying, only the 2 components would be affected. So with this understanding of the memory management subsystems, we now have a high-level view of GMEM design. So if you take a look at the left part of the figure, this is basically how the current situation works. We have this parallel address space exposed to the upper-level application so that making the programmers difficult to write their program. The GPU address is not the same as the CPU address, so you cannot use them on different accelerators or different processors. And underneath the CPU address, you have the Linux core MM, which is basically 80,000 lines of code, as well as the GPU address space, underlying of which has over 70,000 lines of code from your GPU driver. And these 2 memory subsystems, they are independent, so they don't really coordinate. If we look at the right side of the figure, which is currently the GMEM's design, we have a unified address space on top of the system so that the application can use it. And underneath the unified address space, we have a Linux core MM and a GMEM layer that coordinates deeply inside the Linux MM. So for any accelerator, and here we use the GPU as an example, it only takes like 100 lines of code simply to call the GMEM API interface, as well as registering the underlying dev architecture specific functions. So here we have the 4 different design principles. The first design principle is that we only provide high-level APIs, just as the GMEM API, so that device drivers don't need to reinvent all these hardware-independent mechanisms. The second principle is that we want to decouple the low-level MMU handling. And just as registering the device-specific architecture functions, because current Linux design, you can only register different CPU architecture functions, but it is not really scalable or extendable to the accelerators. And the third and the fourth is basically registering their own MMU functions so that we don't limit your microarchitecture design, and we coordinate multiple page tables within each address space. And we would have this question about comparing against the current situation. Like, here's already a solution named Linux HMM, which is in short for heterogeneous memory management. And the question is, why not just use it? So in one sentence, the problem is that HMM does help collaborations between device drivers and Linux MM. But HMM cannot prevent reinventing your memory mechanisms. So we take a look at this diagram, and the left part of the diagram is basically your application's malloc, your system call, and your Linux MM. And we see that HMM only provides 2 mechanisms. One mechanism is the MMU notifier, which is triggered at the time of some certain Linux MM events. So if your device driver is using HMM, you may register some functions to be triggered at the time of certain Linux MM events. So that allows you to coordinate with Linux MM easier. And the second mechanism of HMM is handle MM fault, which is simply a better version of get user pages. So you can see HMM does not prevent you from writing your MM code. And if you take a look at the open sourced NVIDIA UVM driver, they do support HMM. But the support part of the HMM still implements the whole mechanisms. And the second question would be, why not just use a cache coherent bus between the CPU and the accelerator? So for example, we have the CXL, which supports cache coherent accesses between the CPU and accelerators. And we also have this NVLink. As you guys know, it supports C2C connection between the GPU and CPU. But here is a terrible bug that I've learned when I worked at NVIDIA, that it was reported by the IBM, because NVIDIA sells their hardware to the IBM. So they collaborate with IBM and build this supercomputer that connects both the P9 CPU and the Volta GPU with NVLink. And the bug basically says, when I trigger a page fault from my GPU node, the operating system populates CPU's DDR pages corresponding to that GPU page fault. So your GPU then continues to use the slow bandwidth from the CPU node. And that's a terrible bug, and it's only because the operating system is not aware of the GPU node. And GMEM would act differently because it makes the operating system aware of the accelerator nodes. So your NUMA nodes is not the same. It's not like all DDR and all GPU nodes are the same. So data by default will be preferably faulted on the GPU node, and it will provide memory hints so that user can proactively prefetch their data. And lastly, GMEM will allow the user to decide between remote access or fault-driven migration. So the last point is a little bit subtle to understand, but in reality, we have this two different kinds of applications. And the first kind is the applications that may sparsely access memory with a very large memory footprint, which is, for example, the recommender system. The recommendation system uses a large embedding cache that cannot really fit in the GPU HBM. And that's why we have this Grace Hopper design that allows you to put your huge embedding cache in the CPU part. But in the remote access part, you basically accessing the memory just one time, so you can tolerate the small bandwidth over the bus. But on the other kinds of applications, you may want to just fetch the data from the slow CPU DRAM to your HBM so that you can access local memory with much higher bandwidth. And now we can take a look at GMEM's implementation. And this is basically, we're just trying to give you an overview of this because we're not going to dig deeper. So GMEM provides a unified virtual address space by changing the struct a little bit. We're adding a list inside the struct, which points to the address space in Linux. And now we have a pointer list that is basically including all the accelerators attached to this process so that your applications may use. And each accelerator has their registered MMU functions so that anytime when there is any page table changes and we need to coordinate between the page tables, the underlying GMEM mechanism, we're trying to maintain a coherent mappings between these page tables using these MMU functions registered by the accelerator drivers. And the core of GMEM is the logical page table, which we borrowed the design from FreeBSD, that we borrowed the VM object that really decouples the hardware independent layer and the CPU microarchitecture specific layer. This is different from Linux, as Linux is using a page table worker function that basically fixes how you maintain the page tables. But borrowing the design from FreeBSD really allows us to further decouple it so that we can put accelerators inside the processing. Okay, so here are the key features of GMEM. The first key feature is the enhanced programmability, which we share the CPU and accelerator pointers, and we allow transparent memory over subscription and waiving the OOM issue. The second feature is debloating the redundant memory management code. And this not only includes the user level malloc development, but also includes the driver level. And ultimately, we provide some user-guided heterogeneous memory hints. So we not only have this design and implementation, and today I'm also going to give you some preliminary evaluation results. The first evaluation we want to look at is how the programmability looks like. And here on the slide is a pseudocode that I wrote, basically trying to calculating the matrix multiplication of two buffers, which are A and B, and generate the results in buffer C and read it from the CPU. So we start by using the malloc just as how you write your normal C++ program. We malloc 3 buffers for A and B and C. And these pointers are now shareable between your CPU and accelerators. And secondly, if you look at the generate random, these two statements, they are trying to generate some random numbers inside buffer A and B using the CPU. And then after these two generate random statements, we have this statement which is named InQ kernel, where we are launching an accelerator kernel to calculate the matrix multiplication between A and B, writing the results to buffer C. And it can be done directly. There's no explicit memory copying. There's no device-specific buffer. And after that, we also write this 3 HM device, which is GMEM's version of user-guided memory hints. that we are trying to prefetch asynchronously the 3 buffers to the accelerators. So if you guys have written any CUDA code, you may understand that launching an accelerator's kernel is non-blocking when you write the CPU code. So when you enqueue the kernel, the matrix multiplication kernel, it will return before the execution finishes. It returns only when the task is submitted, and the task is now executing in parallel. So after that, the 3 memory prefetching will just run concurrently with the computation. So looking at the right diagram of the slide, GMEM actually presents an easy overlapping between the communication and the computation. Because there are 2 streams. One stream is calculating the matrix multiplication. The other stream is prefetching the data. You don't need to worry about the order, like whether the data prefetching of A and B and C are executed before the matrix multiplication. You just don't need to worry about it. You just throw them into 2 threads and then issuing a synchronized barrier, and then the underlying GMEM system is going to guarantee the correctness. And this is because GMEM features a concurrent page fault mechanism, so that when the computation is executed and the data is not prefetched yet, GMEM will fault the data. And if the prefetch has done, then there's no page fault. So we also look at the basic performance of the memory management system and the malloc library. So we tested some memory-sensitive applications, including Redis or GCC from the spec 2017. They all have like less than 1% performance penalty. And this is done with a Linux system that features GMEM. We also put the malloc library on PyTorch running on the GMEM, and we see that with the GPT, like GPT-2, we ran a training of the large language model, and we found that the average latency of malloc is like 3 times faster. And we also did a test on the operating system called bloating. And we tested this on Huawei's AI accelerator, which is named ASIN NPU. The first row basically shows currently there are 30,000 lines of code in the NPU driver, simply for the memory management part. And when it is developed on a GMEM system, it only takes like 30 lines of code to call the GMEM API. The high-level API really waves reinventing the memory management mechanisms. And there also includes another 2,000 lines of code for the underlying MMU functions to be registered. So it reduces the development effort by 90%. We also tested it with the how does it behave in real applications, how does it solve the memory fragmentation issue. So we use this application, which is a protein folding prediction, which you can see this as an AlphaFold variant. The GMEM allows it to use more HBM so that the problem size is 25% larger. So it can process larger larger sequence of proteins. And this does not involve anything with memory over subscription. It's simply defragmenting memory. And the end-to-end inference speed is also improved. But this is kind of surprising. And we found that this is because it takes a lot of time to compile the accelerator kernels. So with more memory, this part is accelerated. And we're also applying GMEM to enhance the large language model inference throughput. So stay tuned for future results. GMEM also enables a transparent memory over subscription. And in one sentence, a 32 gigabytes HBM NPU was able to train a 52 billion parameters LLM model with only 2 lines of code changes in the AI framework. And it oversubscribed 1 terabyte of CPU DDR, and it's powered by the GMEM. So we also made some comparison between GMEM and NVIDIA's UVM driver, but we are not releasing the numbers now. But the numbers are quite convincing, quite positive. So to conclude our talk, GMEM solves the wide growth of memory service code. This not only includes your accelerator memory management in your device drivers. So at this time, the Linux MM simply works for your accelerator. And also, we prevent AI platforms to write further malloc code. And this malloc code in PyTorch, in TensorFlow, they don't really work well. So you are free to choose whatever malloc code you want. Like, you can use tcmalloc, you can use jemalloc. And GMEM will be the core of AI infrastructure that enhances the programmability with a unified virtual address space, faster malloc speed, better memory fragmentation issue, and all the other performance improvement techniques. So the roadmap of open sourcing GMEM is basically, you can already have the preliminary code that's available online. We also call for contribution because GMEM ultimately is a memory management change in a Linux. But we want device drivers, we want hardware vendors to use it so that their drivers can depend on the high-level API of GMEM. And we also want to further improve the GMEM design. So we need your input from accelerator vendors. And here's a barcode that you can scan, and you will go to the GitHub repo that contains GMEM code. And you can also subscribe our mail list, including the thick compute and thick kernel. So that's the end of my talk, and I'm ready to answer questions.